Hey everyone, what we saw today in the lab was that when things are angularly accelerating and a torque is causing those things to rotate and causing them to spin faster or slower, the amount and the rate at which they increase or decrease their acceleration all depends on the mass and where the mass is located, which we coined the term moment of inertia. So I'm going to do a couple example problems for calculating moments of inertia, and we're going to see how these work out for us. We're going to use these two right here. We're going to have a axis point be right at the center for the first scenario, and then we're going to make the axis point mass 3 down there in the bottom. You can see how massive each mass is and the distance between each of those. So let's set this up and show how to calculate each. So for example 1 here, I have the 2 kilogram masses that are in the corners in blue, and I have the 4 kilogram masses in green at the other corners. I've got the distances between each of those, and if I want to calculate the moment of inertia for the system rotating about our axis point, which is that x, so if this whole thing spins around the x, I can calculate moments of inertia with the capital letter I. And what I want to do is find the sum of each mass times their distance from the center point. And we square the distance for each of the masses to calculate their moments of inertia. Units for this are going to be kilograms for mass and meters squared for squaring the distance from the axis. So kilograms meters squared is your new mass equivalent for rotating inertia. So let's put in all the values that we have. So the 2 kilogram mass is an r distance away from this pivot point. That r distance is 1 meter down and a half a meter over. So if you do our hypotenuse there, you get 1 meter squared plus a half a meter squared. Square root will give you the r value. So the r value ends up being 1.12 meters, and we got to square that. So if you look at that for all the masses, now I'm going to do that for mass 2. Mass 2 is 4 kilograms. Multiplied by that same distance, 1.12 meters, and I've got to square it. Plus mass 3, plus mass 4. And so I'll let you work out all the details on that, and you should get around 15 kilograms meters squared is the moment of inertia of a mass that is rotating about the center point. Think of this iPad as it spins around a center point. That would be the moment of inertia of this setup. Now let's try the second example where I switch the axis. This time I'm going to pivot about mass 3. So think again of the iPad, but now I'm going to pivot on one of the corners and see if the moment of inertia changes as we go along with that. So if I do the 4 kilogram down the bottom corner, it is the axis. So 4 kilograms times 0 meters gives us no moment of inertia. Then I've got the 2 kilogram masses. One is 2 meters away, and the other 2 kilogram mass is 1 meter away, plus the other 4 kilogram mass, and its distance is 1 over and 2 up, so that's how far it is from the axis point. So that's 2 squared plus 1 squared, that's the square root of 5 distance away, the square root of 5 meters squared. So now going through and crunching through all our moments of inertia there, you should get a final moment of inertia of 32 kilograms meters squared. So if we look at this scenario, if I rotate around one of the corners with the 4 kilogram mass, the moment of inertia is much higher. It's over double the moment of inertia. So to rotate my iPad from the corner is a lot harder to rotate than it is for the iPad to rotate just about its center point. So just by doing some mathematical interpretations, you can tell which objects have bigger moments. Or like we did with the 2 sticks today, where the masses are placed, you can easily feel which one has a higher moment of inertia versus the other. Let's try this one more time like the problem has set up in the PowerPoint. So instead of rotating around the center or rotating on a mass, let's say that we have an axis that goes like this. So that axis goes right through the middle of this, and we're going to pivot around that axis. So more of like kind of a billboard spinning around, advertising, whatever business you're talking about. So if we want to do that, the nice thing is each of the masses are now a half a meter from the axis point. So if I want to do my moments of inertia and just sum up all the masses and distances, so I'll let you work all that, and what you end up getting is 3 kilograms meters squared for our moment of inertia. Now, another thing that we could ask is, so what happens now if I move my axis all the way over here? So here's my axis, and I want to spin around mass 2 and 4 rather than spinning right through the center. How does that change my moment of inertia? Well, there's 2 ways of setting that up. You can just simply do the moment of inertia for each of the masses the distance away like we've always done. So let's try that real quick. Moment of inertia of those 2 on the axis is now 0. You have a 2 kilogram mass, that's 1 meter away, and you have a 4 kilogram mass, that's 1 meter away. So doing that math real quick, you get 6 kilograms meters squared. But there's a useful theorem out there that helps you do this when you try to pivot about a point that's parallel to the spinning around the center of mass. What we call that is the parallel axis theorem. The parallel axis theorem states that if you want to calculate moment of inertia from any object rotated on an axis parallel to the center of mass, all you have to do is take the moment of the center of mass plus the total mass multiplied by d squared. So let me show you how to use the parallel axis theorem for the problem we just did. So when we rotated about the center of mass, we found that the moment of inertia was 3 kilograms meters squared. But now we're rotating about that endpoint. That endpoint is parallel to the center of mass. So the center of mass rotation was the 3 kilogram meters squared. And now that I'm rotating about this endpoint over here, what we want to do is, okay, since the 2 axes are parallel to each other, I can find the moment about that point to be the moment about the center of mass, which we already know is 3, plus the total mass multiplied by the distance squared, how far away those masses are from the center of mass. So if we do that, the total mass is the 4, the 4, the 2, and the 2. That gives me 12 kilograms, and the distance from the new pivot point to the center of mass is just a half a meter. So doing your math there, half a meter squared multiplied by 12, add that to the moment around the center of mass, and you get the same exact moment of inertia. The parallel axis theorem allows us to calculate moments of inertia a distance away from the moment of the center of mass. And why is that going to be useful? Well, let's look at a situation where the masses are continuous. So in calculating the moment of inertia for, say, this rod here, and if I'm going to pivot on the end of this rod, I need to calculate the mr squared, as you can see above, the mass times radius squared for each little piece of the rod. So I have to calculate the moment of inertia for the mass very close to the pivot, the ones right in the middle, and the ones at the far end of the rod, which means I'm going to have to add up each tiny little chunk of mass at each distance from that axis, which means I'm going to have to integrate all the way through that rod. When objects are given to you that have continuous mass all the way across, they're going to have what we call linear density, which is the mass per unit length. If there was mass throughout the entire area, we use that as sigma, and sigma would be the mass per unit area. But since it's just a rod, it has a certain amount of mass for every chunk of that rod that you take out. So if the whole rod is 1 kilogram for 1 full meter of the stick, if you cut that stick in half, you should have about a half a kilogram for half the stick. That's all that lambda means there for linear density. So let's do this. Let's calculate the moment of inertia for this rod along the axis point, and I'll show you how to do that with integration. Okay, so here we have our rod. We're pivoting about that end point there, and we're pivoting all the mass, the close mass, the far end of the rod, all has to pivot around that X that I drew on the picture. So that means I have to add up each little piece of mass and multiply by r squared all the way down the length. So that means I can find my bounds of integration to be 0 and L. So all the way from having no length of the rod to having the entire length of the rod. But now we have to look at that dm. Over here I've got the relationship that is lambda mass per length. So if I want to solve for mass, that just gives me lambda times L. But the equation doesn't have just mass, it has dm. So I've got to take the derivative of mass, and lambda is a constant, so I leave that alone, and I multiply that by now dl. So dm equals lambda dl. Let's substitute that in. So we substitute that in for dm, we get lambda r squared dl. R is the distance from the pivot, which we can call a length. So I'm going to substitute out the r for an L. And for our integration, I want to pull out anything that's constant, and the lambda is nice and constant. So lambda now leaves me an integral of L squared dl. So L squared dl should be an easy integral for you. That should be 1/3 L cubed. And we're going to put that with our two bounds from 0 to the full length. Remember to put both those bounds in for L. So put 0 in for L, and then use L for the entire length of the rod. And what we end up getting is lambda L cubed over 3 would be the moment of inertia. But let's go back to the definition of what lambda is. Lambda is mass per unit length, L cubed over 3. And you can see I have an L on the top and bottom, which means that the moment of inertia of a rod pivoting at the end point is equal to 1/3 ml squared. So it's very similar to the moments of inertia we calculated for just point masses. It's 1/3 a mass times a distance from the pivot squared. In this case, when we integrated, it just became L squared. But what would change if we pivoted about the center of the rod? So if our axis now is at the center of the rod, our bounds of integration are going to change here. I can go to the right and get that half of the rod, or I can go to the left and get the other half of the rod. So my bounds are going to be negative L over 2 to positive L over 2 for half the length of the rod. Again, we'll substitute in our lambda dl. So lambda L squared dl needs to be integrated again, which will give us the same thing we had before, lambda, which gives us lambda 1/3 L cubed. But now we have to evaluate that between our two new bounds. So when we evaluate that between our two new bounds, I'm going to get 1/3 times L over 2 squared minus 1/3 negative L over 2 squared. And if you evaluate that out, you'll get, so you get lambda L cubed over 24 minus L cubed over 24, which is really just adding the two of those, so 2 24ths end up being lambda 1/12 L cubed. However, remember that lambda is just the definition of mass per unit length, so mass per unit length times 1/12 L cubed knocks out one of my L's, and I'm left with 1/12 ml squared. Is the moment of inertia of the rod, but now this as it pivots at the center. So you might be asking yourself, alright, I could have any object, I could have many shapes. I'm going to have to integrate every single moment of inertia every single time I do this? And my answer to you is yes, you could. However, if you check in your books at table 9.1, there is a table listed for several objects that have uniform shapes, and they've already calculated the moments of inertia for them, like the thin cylindrical shell. It's just mr squared. The solid cylinder is 1/2 mr squared. You can see if there's a thick wall, you get the hollow cylinder about its axis. Let's go over to the rods. If I rotate about the end point, you can see my moment of inertia here is 1/3 ml squared. If I rotate about the center point, 1/12 ml squared. How about over here? A spherical shell where all the mass is on the outside. So basically a hollow sphere. It's 2/3 mr squared. Solid spheres give you 2/5. Do you have to memorize these? No, you can use them for your homework. And most of the time, either in a problem, I've seen them give it to you in an AP test. So most of the time, the moments will usually be given to you, but here's a quick guide to refer to if you ever need common masses that are rotating. Let's do one last thing here. Let's find the moment of inertia of the rod again, but this time let's use the parallel axis theorem. Alright, so if we want to use parallel axis theorem says that you take the moment at any point that you want, you take the moment about the center of mass, and you add an md squared, d being the distance from the center of mass to whatever point you're pivoting. Well, I know the center of mass for a rod is 1/12 ml squared. And I'm going to add that to the mass of the rod, multiplied by the distance from the center of mass to my new pivot point, which I'm going to pick as my endpoint. So really, the distance there is only half L, and don't forget to square it. So if I do a half L squared, I'm going to get L squared over 4, which gives me L squared over 4. And if I take a 12th plus a 4th, I end up getting 1/3 ml squared, which is what we exactly calculated through our integration. So if you don't want to deal with integration and the parallel axis theorem makes sense to you, then I've just found the moment of inertia about the endpoint, because that endpoint is a parallel axis to the center of mass. So there's another way of setting up and calculating moments of inertia. So that brings us back to what we did in our demonstration today. If lightsabers actually were massive, so if light actually had mass, which of these two would be easier to rotate? And if you pivot the double lightsaber in the middle, the moment of inertia is 1/12 ml squared, versus a long sword where you pivot about the end point, that's 1/3 ml squared. So it's actually easier to rotate the lightsaber about the middle than it is to grab it on the end and rotate it over here. It takes a lot more effort to rotate something about its end point with all that mass away from the pivot. It's a lot easier to rotate when there's equal distance between your two masses. All right, go back and look at what we've done in the video. Do some of those examples again. Maybe make up your own example, but calculating moments of inertia will help us calculate the torques and angular accelerations of systems.